All right, so again, next time we will try to get the Adrian Peterson simulation to work out. In the meantime, I will, besides what was asked for, show you pictures of some graphs. I will share with you his rushing stats from the 2012 season. It was an amazing season. He came in second place as far as the all-time number of yards for a season. 2,097 yards is what he got, and Eric Dickerson from about 30 years ago got 2,105. So he almost beat that, but I went through, I gathered this data myself, by the way. I didn't download it. I went through every single game and like tabulated his rushes in every single game for the entire season, and there was like 348 of them. So, yeah, it took a while, but that was my idea of fun for that. Okay. I mean, I don't like it taking a while, but I was so excited about getting to the end and doing various math things with it that I still enjoyed it. So we ended last time with this general formula for a confidence interval. Here I go, I'll say it again. I probably will say this pretty much every day from now on to the rest of the semester. Now you may get sick of it, but listen every single time anyway, because you got to get the point. You got to understand what this is for. What's the big idea? What's the big picture setting for this? Again, you've got a population. You'd like to know some information about that population, a population parameter value, like a mean. Or a population proportion, or a population standard deviation. Or even if it's two variables, maybe even a slope of a population regression line. That's what we'll do in chapter 10. But we only have sample information. We only gather data about a simple random sample, at least that's what we assume. In reality, people rarely actually do simple random samples. It's just too hard, especially if your population is humongous. But to keep the math simple, we assume simple random sampling. And based on that sample, we get a statistic value like x bar, or like a p hat, or like a sample slope of a regression line per sample. Those are all statistics. If we had a different sample, we'd get different values. The sampling distributions of those statistics tell us what to expect about the variation in those statistics values if we did sampling over and over and over again. But in practice, you only do one sample, and you calculate one statistic, and in this case, again, you want to create this confidence interval, not just a one-number point estimate, but an interval estimate to give yourself some cushion. And you want to feel pretty confident that the true parameter value, in this case mu, is in there. Confidence intervals often, though not always, take this general form. Actually, for us, they will always take that form. They don't take that form, for example, when you're trying to estimate population standard deviations or variances. But we will not be doing that because it just takes us too far afield from the main content. Most confidence intervals, in fact all the ones that we deal with in this class, have this same general form, some point estimate, plus or minus some margin of error. I will not typically write mo, I'll typically just write m like the book. X bar, when we're estimating mu, is going to be our point estimate. If we were trying to estimate p, a population proportion, p hat would be our point estimate. So we've got the point estimate there, we go plus or minus. There's your margin of error. It's always a special z value, denoted z star in our book. Actually, in other books it uses a different notation. But in our book, it's z star. The star is not a number. It's not a power. It's just a signifier to sort of say this is a special number. That's basically all it means in our book. This whole thing, z star, represents one number. For 95% confidence, it's 1.96. That's what you use. This number right there, we've seen that before. That's the standard deviation of the sampling distribution of x bar. So you always take this special number times that standard deviation. The special number, the z star, so far I've just told you to use 1.96 if you want 95% confidence. If you go to a different table in the book, it's in the back of the book. It's a t-distribution table. In our book, it's labeled Table D, at the very back of the book. And if you look at the very bottom of that table, you'll see where to find z star for various levels of confidence C. And if you want 95% confidence in your interval, z star is 1.96. Other common confidence levels to use are 99%, and z star is 2.576, and 90%, and z star is 1.645. Those are the three most common confidence levels to use. Though, there are more that could be used. Although I've never heard of anybody using 50, 60, 70, or even 80% confidence. That just seems too low. Once in a while, you might be more likely to hear somebody say they want 99.9% confidence. So it's more likely to use the other extreme, the high extreme, than the low extreme. For the moment, in this table, we're ignoring everything else. We're just focused on the bottom. So based on the statement of the problem, based on the confidence level you want, you get these different values for z star. It should be intuitive, based on what I said before break, before the quiz, that if you want more confidence, you need a bigger interval, and therefore z star must be bigger. Sigma over square root of n is not going to change. Sigma is the population standard deviation. That's fixed. It's a parameter. It's unknown, but we pretend we know it. N is the sample size. You are thinking about a fixed sample size here when you use this formula. Z star is the only thing that can change. And look, if you want more confidence, you go to the right in this table. To get more confidence, the values of z star get bigger and bigger. Actually, z star can be figured out from the standard normal table as well, but you have to do more work. This is easier. If you want to use the standard normal table to find z star, zoom in with the camera here. Look in your book if you've got your book, in the front cover. If you wanted to find z star for 95% confidence, that means you're looking for the value of z star so that the area under the graph between negative z star and positive z star is 0.95, as close as possible. That area is 0.95. Now we know based on the 68, 95, 99.7 rule that z star must be close to 2 because of that. However, 1.96 is a little bit better. If that area is 95%, that leaves 5% for the tails, since because of the symmetry, each of those tails is 2.5% of the area. You add those up and you get 97.5% of the area to the left of z star. So that means in this table you need to look for 0.975 as close as possible. I see it exactly there, right there, 0.9750. Actually, that's an approximation, but don't worry about it. And it does correspond to z equals 1.96. Okay? So you can figure it out with the standard normal table based on it giving you areas to the left of numbers, but you have to do some thinking, okay, before you can figure it out in there. So it's definitely easier to use the t-distribution table at the very bottom. That's the easier way to go, and that's fine. But I want you to know you could do it with this too. Stop me if you have any questions, if you want me to clarify something. If you'd like to get this. Well, let's try another one. Let's try another example. Let's try to confirm the 90% one. Although this one's going to involve a little interpolation. Let's try to confirm the z star is about 1.645 for 90% confidence. This is the bottom of the t-distribution. That is what tells you what z star should be if you want 90% confidence. That's the quickest way to get it. If you wanted to find it with table A, now you want to find z star so that the area between negative z star and positive z star is the confidence level, 90%. Because of this, that leaves 10% for the tails, and because of symmetry, this would now be a 5% instead of a 2.5%. And then these two numbers would add up to 95%. So That means if you want the z star for a 90% confidence interval, you got to look for 0.95 in the table. There is no 0.95, but these two are equally close right there. It's a 0.9495. It's helpful if you look in your book, and a 0.9505. I know this is too small for people in the back. 0.95 is halfway between those. The corresponding z, therefore, should be approximately halfway between 1.64 and 1.65. 1.645 is halfway between. Actually, that interpolation by averaging is not exactly right, because the curve is not a horizontal line, but it's close enough. Halfway between 1.64 and 1.65 is 1.645, and that's the z star to use for 90% confidence. Yeah, I think that was worth looking at for a different example. It's the Central Limit Theorem that basically justifies this. We're thinking about the sampling distribution for x bar. I had some probability statements at the end of the last class period where I was using the Central Limit Theorem related to x bar to help us figure out the formula for the confidence interval. So that's the basic thing I want you to know about that. The Central Limit Theorem is what justifies this, approximately at least. How should it be interpreted? That's what we want to focus on now for about 5 minutes. And then we'll move on to the next topic. This is important. For a level C confidence interval, estimate a population parameter. Just for the sake of argument, for your imagination's sake, pretend C is the most common thing to use. Pretend it's 95%. So I will state this for a general C. The confidence level, the 95%, for example, could be interpreted as a probability if you think about it as being the probability that you will capture the true parameter value, mu, for example, before you actually do your sampling. If you say to yourself, I am about to collect a random sample from my population and calculate x bar and then calculate a 95% confidence interval. I'm about to do that. I'm about to use z star equals 1.96. And I'm saying I know what sigma is. I know what the population standard deviation is. What is the probability that when I do that, I will capture mu? It's valid to think of it as a probability in that sense. However, theoretically speaking, this is a very subtle point here. After sampling and computing is done, the confidence in it level, like the 95%, is technically, no longer a probability. Why? Because all the random chance is gone. There's no random sampling anymore. You've already done your random sampling. So all the chance involved is gone. Either mu is in the interval or it's not. Theoretically speaking. However, from a practical standpoint, it's not a real big deal in my mind, at least, to think of the confidence level, the 95%, as being still like betting odds. If you had to bet, not that I'm advocating betting, but if you had to bet whether mu's in there, and you calculated a 95% confidence interval, and somebody didn't know the true value of mu and they just weren't telling you, you'd be pretty safe betting money on mu being in there if you're doing 95% confidence. If you're for some crazy reason doing 50% confidence, then it's a 50-50 bet. But nobody ever does that. Okay? So you can still effectively, from a practical standpoint, think of it as probability, but I'm on shaky ground saying that, okay? It's really more like betting odds. That's why we use this new word. We're confident. We're 95% confident that mu has been captured. That's the technical reason for the new word. We kind of want to avoid the word probability once we've done the sampling. So we just use 95 or 99% confidence is the way we describe how confident that we are. It is related to probability, but again, after the sampling, technically speaking, it's not a probability anymore because there's no more randomness. You calculated your sample and your statistic. You gathered your sample and your statistic. Here's another way to think of the 95% or 99%. If we repeated simple random samples of the same size from the same population and got many, many different confidence intervals, and you will get different ones for different samples because X bar is not going to be the same. In fact, you could even say the endpoints, the left and right endpoints are random variables. Very much related to X bars being a random variable. The confidence level reflects how often the various intervals would capture the true parameter value. If you're calculating 95% confidence intervals over and over and over and over again, hundreds or thousands of times, which you probably only do with simulation or with theory, about 95% of the time the truth will be in the interval, the true parameter value. But, like I said, I don't know, 5-10 minutes ago, make sure you realize that no one knows the true value of the population parameter. It's unknown typically and oftentimes unknowable. Nobody could possibly know. In fact, it might, here's a dirty little secret, it might even be changing. Wait, I thought parameters are fixed numbers. Yeah, they are in theory. But in reality, they could be changing, like take the average height or the average weight of everybody in the country. You're changing your height slightly and your weight slightly all the time. You're growing, or maybe you're shrinking when you get old like me. You're certainly changing your weight all the time. Even breathing in and out causes your weight to change. You're perspirating a tiny bit. Can't feel it. Sweat evaporates. You change your weight all the time. So since everybody's individual weight is changing, the mean weight's changing too. Not by very much, but technically a tiny amount. So in reality, parameters might not really be constant. So there's another way they can be unknowable. I suppose if you say we're talking about a parameter value at a fixed instant in time, then I guess it could be a fixed number. But once that fixed instant in time is passed, now you're past that. And you're no longer really estimating that so much as some other value when you take your sample. Okay? These are real subtle technical points. I think they are good to know. And you should know them for quizzes, tests, and interpretation on problems sometimes. Can I clarify anything? Okay? We're going to do this stuff over and over and over again for the rest of the course. It's not going away. Same with the rest of the subject for today. Hypothesis testing, also known as tests of significance. About a 10-minute introduction to it here. This is also inferential statistics, just like confidence intervals are. We're taking sample information and trying to say something about the wider population. That's inference, part of inferential statistics. These are the two main big idea branches for inferential statistics that we teach in undergraduate stats courses like this. There's the confidence intervals, and then there's the hypothesis testing, also known as tests of significance. The hypothesis testing, the test of significance, is much more challenging than the confidence intervals. Okay? We're going to be doing this over and over again for the rest of the semester too. This is hard. The confidence interval formulas are pretty easy actually. They can get messy. It's easy to make mistakes sometimes. But if you don't make a mistake, if you can deal with the messiness, it's just rote computation essentially. The interpretation is a little trickier. With the hypothesis testing, it's definitely tougher. Lots of ideas going on with this. Here's a situation where you might do hypothesis testing. An example I took out of the book. The Survey of Study Habits and Attitudes, SSHA, is a psychological test that measures attitudes towards school and study habits. Okay, so this is some psychology thing. The mean score for US college students is 115, and the standard deviation is about 30. What does that number mean? I don't know for sure. It said the scale was 0 to 200, so I suppose 115 and being above 100 is slightly positive at least. Maybe a score below 100 is a negative attitude. A teacher suspects that adult students have better attitudes and gives the SSHA to a random sample of 36 adult students who are at least 30 years old. I'm going to give you this problem, though I did modify it slightly from the book. Probably not for this assignment, but for a future assignment. How should we, or the teacher, set up a test to test this teacher's hypothesis, this theory that the teacher has that adult students have a better attitude towards school? That's one question. Another question: if she found the mean score for her random sample to be higher than 115, if her x bar was higher than 115, what would that mean about her hypothesis? Is her hypothesis right or not? Here's the way we're going to do the setup for the teacher's test. Okay? We're first going to define the parameter we're trying to test. Step 1, define the parameter being tested. Okay, in this case, it's a population mean. Mu equals the true mean score on this test for all college students, say, in the country. This is US college students here. The true mean score on SSHA, Survey of Study Habits and Attitudes test, for all US college students. Now, they didn't specify in the problem statement, and since I pretty much copied it here, I'm not specifying here whether these are traditional undergrads or traditional age groups, 18 to 22, or whether this group includes adult students above age 30 as well. By the way, sometimes people do go to school between 22 and 30 as well. Sort of halfway, sort of between the traditional college age and sort of the more adult student population, more typical adult student population. Okay, so that's the first thing to do. I want you to do this. I want you to define your parameters. You want to know what you're trying to test here. Second thing is you state your hypotheses. State the two hypotheses, theories that are possible. One is called the null hypothesis and is labeled H sub 0. That's the null hypothesis. And one is called the alternative hypothesis, also sometimes called the research hypothesis. In some books they label this with an H1 instead of an H0. But in our book it's labeled H sub A, the letter A standing for alternative. And we will call this the alternative hypothesis. Again, that's sometimes called the research hypothesis. Most often, in this kind of problem, this kind of setting, the researcher, in this case the teacher, is trying to test the alternative hypothesis. That's their hypothesis. That's what they think is right. This teacher has a theory. She suspects adult students score higher than 115. Give SSH to, let's see, where does it say it? Suspects adult students have better attitudes. So their score should be higher than 115, their mean score. Actually, that tells me I did something wrong here. This is not the mean score on the SSHA test for all US college students. It's for all adult. US college students. Age 30 and above. Age greater than or equal to 30 is what that says. Okay, that's really what she's testing. So I made a mistake there first. She's testing that. She thinks that number is higher than 115. Got that? She's being told that for all US students, maybe just traditional undergrads, maybe every college student, that the mean is 115. But she thinks, she's got a theory, she's got a hypothesis that adult students, age 30 and above, score high. The alternative hypothesis, that's her theory. Mu is greater than 115. Technically speaking, the null hypothesis is the opposite of that statement. Mu is less than or equal to 115. It would be the opposite. However, in doing the test, in testing her hypothesis, we will end up assuming the null is true at its boundary value, equal to 115, not less than or equal to 115. Turns out to be fine to do the test that way, which for reasons I'm not going to get into right now. So to keep things simpler with our concepts and with our calculations, we do not write the null hypothesis as a less than or equal to here. We write it as an equal to. That's the setup. Define the parameter being tested. Mu is the true mean score on SSHA test for all adult US college students age 30 or above. That's the parameter we're testing. We're stating hypotheses. These are the two things you should do to set up the hypotheses, the test of the hypothesis. Second question. If she found that the mean score for her simple random sample was higher than 115, if her X bar score, sample mean score, was higher than 115, what would that tell you about her hypothesis? Is she right or not? Is the answer yes or no? Or is this a trick question? If she gets an X bar of 116, 117, 118, 119, does that mean she's right or not? Or is it a trick question? It's actually a trick question. What? How could it be a trick question? Her hypothesis might be right and might be wrong. Still, here's the key. The further X bar is higher than 115, the stronger the evidence for her hypothesis and against the null. So it's not just a matter of it being bigger than 115. It's got to be a fair amount bigger than 115. Because maybe, if it's just a small amount bigger than 115, that could happen by chance, just because of the 36 students she happened to give the test to. When it's far enough away, that's called statistically significant. And that's stronger evidence that she's right. All right, see you next time.